What if I told you the future of supercomputing looks less like microchips and more like braiding hair? Yes, literally tying knots in space and time. This bizarre technique, called topological quantum computing, is actually our best shot at building quantum computers that don't constantly crash from microscopic errors. If we master this, we finally unlock the true power of quantum machines, simulating complex molecules for instant drug discovery and creating truly unhackable encryption. To understand why this is so revolutionary, we first need to look at the problem with standard quantum computers. They rely on regular qubits, which are incredibly fragile. A tiny change in temperature or a stray magnetic field causes decoherence. Essentially, the qubit forgets its quantum state and your calculation is ruined. It's like trying to build a house of cards in a hurricane. Enter topological quantum computing. Instead of fragile, isolated qubits, we use exotic quasiparticles called anyons. Unlike standard particles like electrons or photons, anyons can only exist in two-dimensional spaces. And they have a mind-bending property: when you swap their positions, they remember the swap. Their history is recorded in their quantum state. This brings us to the magic of braiding. Imagine anyons moving around each other over time. If we trace their paths in 3D spacetime, with time being the third dimension, their trajectories literally weave around each other, forming complex braids or knots. Different braid patterns correspond to different logic gates in a quantum circuit. You are computing by tying quantum knots. Why is this better? Because topology is robust. Think about a knotted shoelace. If you wiggle the string a little bit, or even drop it, the knot doesn't untie itself. In the same way, local noise or microscopic interference cannot change the overall topological braid of the anyons. Your quantum information is fundamentally protected by the geometry of the universe itself. We call this topological protection. So, how do we build this? Scientists, heavily backed by companies like Microsoft, are trying to coax these anyons into existence using exotic states of matter, specifically looking for particles called Majorana fermions at the ends of nanowires. It's an incredibly difficult engineering challenge, as it requires temperatures near absolute zero and pristine materials. While we are still in the early days of realizing a fully functional topological quantum computer, the potential is undeniable. By transforming the delicate art of quantum physics into the robust mathematics of knots, we are paving the way for the ultimate computing revolution. The future isn't just quantum, it's beautifully braided.